We're in pre-calculus proving trigonometric identities. And what that means is we're looking at half of an equation and the other half of the equation, trying to make them stay the same, make them express the same thing. You remember some of our identities are things like the sine squared of theta plus the cosine squared of theta equals 1. In other words, the left side is always equal to the right side. In order to prove this identity, we're going to do a two-column proof, just like we did in geometry. The left side is the statement. The right side is the reason. And we're always going to start with the more complicated part. Would you guys agree the left side of this is more complicated than the right side? Okay, so I'm going to write that in. Cosecant of theta times the cosine squared of theta plus the sine of theta. And because I've just written that, that's what was given. Now I need to turn this whole thing into cosecant all by itself. So probably one of the easiest things to do would be for me to get them all in terms of sines and cosines. Cosecant we can change into what? Good. So 1 over sine theta, it's still being multiplied by cosine squared theta plus sine theta. And what I just did there is the reciprocal property. If I wanted to be really specific, what I could write is substitution of the reciprocal property. Reciprocal ID. Now, how many terms do I have on the left?
3.
Almost. Further away.
2.
2. These being multiplied make it 1 term. This being added adds a second term. So I've got 2 terms, but my answer is supposed to be a single term. So I need to somehow combine these 2 things. First thing I'm going to do is treat this like a fraction. I'm going to multiply this times this, getting me the cosine squared over sine. And I still have sine over here. What I did is I just simplified really there, or multiplied fraction. Now, as I said, I want to have a single term. I've now got 2 terms. If this is a fraction and I want to combine it with this other quote unquote fraction, what do I need? You can only add 2 fractions when they have common denominator. So what if I multiply this one by sine over sine? What that's going to give me is cosine squared theta over sine plus sine squared theta over sine. Sure, go ahead. The far switch will make it better contrast up there. And now our whole objective here was that these 2 fractions have a same denominator. Do they now?
Yes.
So that means I can combine them and create cosine squared theta plus sine squared theta all over a single sine theta. And if I've got cosine plus sine, cosine squared plus sine squared, what does that mean? 1, right? So I can treat this as 1 over sine theta, which I can then quickly change into cosecant theta. Now I've run out of space here. Let's see if I can make it easier to see here. What was this step to go from here in the pencil to this one? It's really that purple line.
Multiplication.
Yeah, it's multiplying by 1 in the form of sine over sine. What do you call it when you've got 2 fractions with a common denominator and you bring them together? I would just say fraction addition. It's adding fractions. That's the way you do it. And then I took cosine squared plus sine squared, and I changed that into 1. Good. And that left me with 1 over sine that I turned into cosecant. And that's called the reciprocal identity. Now, I know people don't like to waste paper, and I've given you some space, and you can fit most of these in. But if you'd like some blank paper or graph paper and you want to write this all out, I think you'll have a better experience with it. Let's take a look at number 2. Which side do you want to work with, the left side or the right side? You like the left?
Yeah,
Anybody else like the right instead?
like the right.
Is this one term or two? One term. Is this one term or two? It's two because it's separated by addition or subtraction. So if I started with this, my goal would be to combine terms. If I started with this, my goal would be to strategically uncombine terms. It can work either way. Let's try this one first. We're going to do this one both ways. You guys just watch for a second and decide which way you like better. So we'll start with sine squared y over cosine y. That's our given. Now what should I do? Well, I'm trying to get it to be two different terms, right? So I need to somehow turn this into something minus something. Sine squared y screams out at me. Does that scream out to you? What is it? Pythagorean identity? Right? Didn't we say that sine squared plus cosine squared equals 1? So if I subtract cosine squared from both sides, what I get is that sine squared is equal to 1 minus cosine squared. So I can replace this with 1 minus cosine squared y over cosine y. And that's the Pythagorean identity. How I went from this step to this step? Well, let me show you what I'm going to finish with, and then maybe you'll see how it comes about. This is one of those things where by doing it multiple times, you'll become more familiar with it. I said there were going to be two different ways to do this. This is one of the ways. Having done this, is this one term or two? It's one thing being divided. Terms are things separated by addition or subtraction. You're right that the numerator is two terms, but as a whole object, this whole thing is a single term. I want it to be two different terms. That's my goal over here. So can I separate this to make it two terms?
Yeah.
Can I call it 1 over cosine y?
Yeah.
Minus cosine squared y over cosine y. It's almost like doing it backwards, where you've got the same common denominator, and instead of combining them to make this, we're going backwards. So what do we call that? I'm going to call it fraction addition. It's really unadding, kind of like factoring is unmultiplying. But if you've got the same denominator, you can treat it as 1 over that minus cosine squared over that. Now, what is 1 over cosine?
Yeah.
Secant, right? And that's what we want here. See, we wanted the secant, we got a secant. That seems promising. And I'm only doing one step at a time. That was my reciprocal identity. Can I clean this up a little bit? If I've got cosine squared over cosine, what happens? That cancels, leaving me just with secant y minus cosine of y. And I'm just going to say simplify or reduce. And again, you could, if you wanted to, say that secant y minus cosine y is equal to what I was trying to get to. I made it so that they're the same. What do you think? 5. This is Easy, I can do this. 3, I wouldn't call it easy, but I can do this. 1, I wouldn't call it easy. I wouldn't call it doable. I'd call it something else. Okay, there are 3 things to be successful with this. 1, you must know your identities. We've had a chance to play with those quite a bit. If you have not yet memorized those, please get good at those. The quotient identities, the reciprocal identities, the Pythagorean identities, the even odd identities. We're going to be adding some more on as well. The second thing is you got to be able to work with fractions. If you're struggling with working with fractions, you're going to have trouble with these. And the third is have a eraser handy. You need to exhibit persistence. You need to keep trying at these things. You'll make mistakes, and that's okay. Now, let's come back and try this one again. I said that there's 2 ways we could have done this. I chose to start with this side. What if we had started with secant minus cosine? What would be a good first step? I agree. Get them looking like they're both cosine and sines. That's the reciprocal identity. Now, same idea. We're coming from the right side now to the left. We're starting with 2 terms, things separated by addition or subtraction. We're trying to get to a single term. So what do I have to do with these 2 terms? I got to get them together somehow, right? Well, this is a fraction. How do you add or subtract fractions? You need to have a common what? So let's give this a common denominator. What should we multiply this one by? Well, we can't multiply it by cosine. That'd be illegal, but we can multiply it by cosine over cosine. That's valid to multiply this by something over itself, cosine over cosine. And my description would be multiplied by 1 in the form of cosine y over cosine y. Now that these 2 things have the same denominator, what can I do? Yep, so I can say 1 minus cosine squared y over cosine y, and that's just adding fractions. We're trying to get to sine squared over cosine. We've already got our cosine on the bottom. That looks fine. The top needs to be sine squared. What can we do? Good. We can just swap this out. This is the same as Pythagorean theorem. And so when I say you have to know the identities, that means you have to not only know sine squared theta plus cosine squared theta equals 1, you also have to know what happens if you subtract sine squared. So that the cosine theta squared equals 1 minus sine squared. Or you could have had sine squared theta equals 1 minus cosine squared theta. And you got to be able to have the reciprocal function of these. If I divide everything by sine squared, I get 1 plus cotangent squared equals cosecant squared. And if I divided everything by cosine, I'd get tan squared theta plus 1 equals cosine secant squared theta. You need to know all those versions.
Like you like the work video problem.
This one?
No. No, I mean, number 2, like,
Yeah, let's take a look at number 4. Which side looks more complicated, the left or the right?
to the left.
I'd say the left is a lot more complicated, isn't it? So tan of x times secant of x over tan of x minus tan of x over secant of x. All right. It looks to me like this is 2 terms inside here. I'm trying to get to a single term. I got to clean this up. So what could I do to make these 2 things come together? Common denominator, right? Okay. So one way to think about this would be to change them all into sines and cosines. You guys agree? I could change this into 1 over cosine. This is sine over cosine, sine over cosine, 1 over, and then there's some cleaning up to do. But I'm going to suggest a little strategic way. If I want these two things to combine, forget about changing them into sines and cosines. What does the denominator have to be?
And below cosine.
If I had 1/2 minus 1/3, what would the denominator have to be?
6.
You would multiply both of these things together, right? And say it's going to be a 6. And this one I'd multiply by 3 over 3, and this one I'd multiply by 2 over 2, and that would give me denominators of 6, right? Let's do the same thing. I need my denominator to have a tangent in it. I need my denominator to have a secant in it. So what I'm going to do is I'm going to multiply this left one by secant over secant. That gives me secant squared over secant x tan x. And what do I multiply this right one by? I want this denominator. So I multiply it by tan squared, or tan x, excuse me. I multiplied by 1 equals tan x over tan x, or secant x over secant x. Now, the trick here is you got to keep track of what you're trying to do. If you tried to cancel the things that are on top and bottom, that takes us right back to where we were. We don't want that. We can combine these now. They've got a common denominator. Okay, so that's just addition. And if you want to say of fractions to clarify that we did it with common denominator, that's fine. Nope. So let's do it with numbers here. If I had 1/2 minus 1/3, first I would multiply 3 times this one, 3 on top, 3 on the bottom, and that would give me 3/6. And this one is times 2 and 2, which would give me 2/6. Once I have the common denominator, I can combine them basically into one fraction. It's 3 minus 2/6, which is 1/6. So this top one I multiplied by secant over secant. So the top became a secant squared and the bottom became secant tan. On this side, I wanted the same denominator, secant times tangent. So I multiplied it by tangent over tangent, making this a tangent squared and this secant tangent like I wanted. Now that I've got a common denominator, it's like 3/6 minus 2/6. That's the same as 3 minus 2/6. Now, I would probably get rid of this tangent, right? I'm multiplying by a tangent. There's a tangent in the denominator. So we can cancel that, right? That's just simplifying or reducing. Now what? Let's take a look. What are we trying to get to? We're trying to get to cosine. Do these scream out at you? Secant squared and tangent squared? Do they scream?
Yeah, secant, tangent, and then it's like secant. It's like tangent plus 1 equals secant, right?
Tangent squared plus 1 equals secant squared. Okay, good. Let's do that. So tangent squared plus 1 equals secant squared. So I can replace this with tan squared x plus 1, right? I replaced this one with tan squared x plus 1. And then I left this minus tan squared, right? So that was Pythagorean. And now I've got tan squared x minus tan squared x. Those go away. I'm left with 1 over secant. What do I try and get to? Isn't this the same as cosine of x? because 1 over secant is the same as cosine, or 1 over cosine is the same as secant. That's the reciprocal idea. If you want to be a cool proof writer, you write QED, which means you've proven what you're supposed to.
You have to. Right,
No, you don't have to be cool.
okay.
All right. And then you asked about number 6 as well, right? Do you guys want to take a stab at it first before I go through it?